what actually exists at the center of a black hole tonight. We're going to dismantle an image that's been sitting in your mind since you were a child. A picture you've seen in textbooks, in movies, in cartoons, in every casual conversation about the universe you've ever had. The picture of a black hole, a swirling funnel in the dark, a drain in space, something that pulls things in, crushes them down, and at the very bottom, hidden behind a wall of darkness, there is a tiny point, a grain, a speck, a single dot containing everything that has ever fallen in. That is the picture you have carried with you quietly for years. And tonight, we are going to take that picture apart piece by piece until nothing of it remains. Because here is the strange truth that almost no one tells you. After more than a century of mathematics, after 50 years of observation, after 2 photographs of 2 real black holes hanging on our walls, we still do not know what is at the center of one. Not really. Not in any way that physics can stand behind. The point that sits at the bottom of every diagram you have ever seen is not a discovery. It is a confession. It is the place where our finest equations stop speaking and begin to scream, and the scientists who built those equations admit, quietly, that something has gone deeply wrong. So the real question we are asking tonight is not what is at the center of a black hole. The real question is whether a center exists at all, and if it does, in what sense it exists. And what kind of object, or non-object, or condition of reality could possibly live in a place where space itself folds inward, and time becomes a direction you can no longer choose? Let that question sit with you for a moment. Because the answer, when we finally circle back to it many hours from now, is going to be stranger and more humbling than the cartoon ever was. Tonight, we are going to descend. We are going to fall through layers of understanding, each one larger and stranger than the last, and what we find at the bottom is not going to look like a point at all. It is going to look like something almost no one talks about. Something that may not even be in the universe, in any familiar sense of the word. Something so peculiar that the people who study it for a living disagree about whether it is matter, whether it is geometry, whether it is information, or whether it is, in some unsettling way, you. Before we go any further, if you find this kind of slow, deep exploration calming, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, take a breath, let your shoulders drop, and let us begin the long descent together. On number 1, the drain in the dark, the picture you were handed, we have to start with the lie. Not a cruel lie, a useful one. A lie of convenience, a lie of teaching. The picture of the black hole as a funnel in space, with stars and gas and light spiraling down into a dark mouth, is the first image almost every human being is shown when the subject comes up. You have seen it on book covers. You have seen it in animations. You have seen it in films where the hero stares into one with a heroic frown. It is so familiar that you may have stopped questioning whether it has any relationship to reality at all. And yet that picture is not what a black hole looks like. It is not even close. The funnel you see in diagrams is not a hole in space. It is a metaphor. A specific metaphor, in fact, drawn from a specific equation, in which physicists try to represent the curvature of 4-dimensional spacetime by drawing a 2-dimensional rubber sheet bent downward by a heavy weight. The funnel is the bending of the sheet. It is a teaching aid. It exists only in pictures, never in the universe. If you could actually travel to a black hole, you would not see any funnel at all. You would not see a swirling vortex pulling you in. You would see instead a perfectly black sphere, round, silent, smooth, surrounded by a thin ring of light that has been bent into a halo by gravity so intense it can twist the path of a photon into a circle. You have seen this. You have seen it twice. In April of 2019, the Event Horizon Telescope released the first photograph of a black hole, a colossal beast at the heart of a galaxy called M87, some 55 million light-years away. And in May of 2022, the same team released a photograph of Sagittarius A star, the smaller but closer black hole that sits at the center of our own Milky Way, about 27,000 light-years from where you are sitting right now. Two pictures. Two real observed, documented black holes, and in neither one of them was there a funnel. There was a glowing ring, and inside it, a circle of perfect darkness. That darkness is what we call the shadow. The shadow is not the black hole itself. The shadow is the region of space inside which all paths of light bend so severely that they cannot escape back to your eye. It is a kind of optical hole, a place where the universe has decided to keep its secrets. So let us drop the funnel. Let us drop the drain. Let us drop the swirling vortex. None of those things exist. What exists is a sphere of darkness, and inside that sphere something the photograph cannot tell us about, something no telescope will ever directly see, no matter how powerful we build them. Because the very thing that defines a black hole is that nothing inside it can ever send a signal out. Not light, not radio waves, not gravity itself, not really, not anything you could read with an instrument. The interior is, in the most literal sense, beyond observation. It is the only region of the universe permanently sealed away from us, and yet our equations claim to tell us what is in there. They tell us with confidence. They tell us in numbers. They tell us in geometry. And the central claim of those equations, the headline result, is that at the very middle of every black hole sits a point of infinite density, a singularity, the thing the funnel is supposedly pointing at. But here is where the trouble begins. Because the equations that predict the singularity are the very same equations that, when you actually look at the singularity carefully, fall apart in your hands. They produce infinities. They produce nonsense. They produce a number divided by zero in every term, and the physicists who wrote them down know, all of them know, that when an equation gives you infinity, it is not telling you that infinity is real. It is telling you the equation has stopped working. The singularity is not a feature of the universe. The singularity is a feature of our ignorance. It is a flashing red warning light on the dashboard of physics, and we have been mistaking it for a destination. So let me ask you something personal before we go any deeper. When you first heard about black holes, maybe as a child, maybe in a science class, maybe from a movie, what did you imagine was inside? Did you picture a tunnel to somewhere else? A crushing weight? A door? Or did you, like so many of us, just accept the word singularity without ever wondering what it really meant? I am curious. Take a moment, and if you have a memory of that first image, share it in the comments below. We are about to leave that image behind for good, but it is worth knowing where you started, so you can feel how far we travel from here. On number 2, the equation that broke its own father when Einstein's math predicted monsters. To understand why the singularity is a problem rather than an answer, we have to go back to the beginning. We have to go back to the moment a single human being, sitting in a small office in Berlin during the First World War, finished writing the equation that would haunt physics for the next century. His name was Albert Einstein. The year was 1915. And the equation he had just completed was not about black holes. It was about gravity. Einstein had spent 10 years trying to answer a simple, almost childlike question. What is gravity, really? Newton had described it beautifully 250 years earlier as an invisible force, reaching across space, tugging on every apple, every planet, every star. The math worked. The predictions came true, but Newton himself had admitted he could not explain how the force was transmitted. How does the sun know the Earth is there to pull on? What is the cord between them? Newton refused to guess. He called the question philosophical. He left it alone, and the world left it alone with him for 2.5 centuries. Einstein refused the silence. And what he eventually proposed, after a decade of struggle, was so radical that it took the entire physics community years to fully absorb. Gravity, Einstein said, is not a force. Gravity is geometry. Mass and energy bend the fabric of space and time around them, and what we feel as a pull is simply the bending of the path we are already on. The Earth does not pull you down. The Earth has carved a curve into spacetime, and you are sliding along that curve. The Moon does not feel a force from the Earth. The Moon is following the straightest possible line through a region of space that is no longer flat. Light even falls into curves around heavy objects, because light too must travel through bent geometry. The whole universe, every star and planet and bit of dust, is moving along the bent contours of a fabric you cannot see and cannot touch. This idea, this strange and beautiful idea, is called general relativity. And general relativity is not just a theory. It is one of the most thoroughly tested ideas in the history of human thought. We have tested it in laboratories. We have tested it with atomic clocks flown on airplanes. We have tested it by watching how starlight bends around our sun during eclipses. We have tested it through the orbits of satellites, the timekeeping of the GPS network, the slow precession of the planet Mercury, the falling of mirrors in the LIGO observatories that listen for gravitational waves. Every test general relativity has been given, it has passed. Every prediction it has made, the universe has confirmed. It is, by almost any measure, the most successful description of gravity ever written. And yet, only a few weeks after Einstein published the final form of his equations, in 1915, a young German physicist named Karl Schwarzschild, fighting in the trenches of the Eastern Front, sat down in the spare hours of the war and found an exact solution. He solved Einstein's equations for the simplest possible case, a single point of mass sitting alone in empty space. He sent his work to Einstein by mail from the front. Einstein was astonished. The solution was clean. The solution was simple, but the solution contained something strange. At a certain distance from the central mass, depending on how heavy the mass was, the geometry of spacetime became, in Schwarzschild's words, peculiar. The equations went to infinity, not at the center but at a particular radius around it. A radius below which, the math suggested, nothing could ever escape, not even light. Schwarzschild called this peculiarity a coordinate boundary. Einstein hoped it was an artifact. Neither man, in 1916, fully understood what they were looking at. Schwarzschild died of an illness contracted in the trenches a few months later. He never saw what his solution would become. But the radius he had identified, that mathematical curiosity, that strange ring around a point of mass, would eventually be given a name. It would be called the event horizon, and the object inside it would, decades later in 1967, be christened by an American physicist named John Wheeler with a phrase that has never been forgotten: a black hole. For decades, almost no one believed black holes were real. Einstein himself did not believe they could form. He spent years trying to prove that no actual collection of matter could collapse all the way down to a point of infinite density. He thought the universe would always find some way to stop the collapse. Some pressure, some force, some last-minute reprieve. He died in 1955 still uncertain on the matter. And then, slowly, throughout the second half of the 20th century, the evidence began to pile up. We observed strange compact sources of X-rays. We observed binary star systems, where one partner was invisible but massive. We observed the orbits of stars near the center of our galaxy, moving so fast that whatever they were orbiting had to be millions of times the mass of the sun, crammed into a volume smaller than our solar system. We observed, eventually, gravitational waves from two black holes spiraling together and merging, the chirp of their collision arriving at our detectors in 2015, exactly as Einstein's equations had predicted a century before. And then we took the photographs, 2 of them, real, direct, undeniable. Black holes are real. The equations that predict them are correct. And the equations also predict, at the center of every one of them, a singularity, a point of zero size and infinite density, a place where Einstein's beautiful geometry tears itself in half and refuses to mean anything anymore. The very same equations that have given us GPS satellites and gravitational wave astronomy also give us, at their heart, an answer that is not an answer, a number that is not a number, a description that says, in effect, here is where I stop being a theory. So I want to ask you, when you think about general relativity, do you think of it as a finished theory or as a theory waiting to be replaced? Because we are about to see that even Einstein, with all his genius, was only painting half of a picture. And the other half of that picture, the quantum half, has not yet been combined with his. Which side do you think will turn out to be more right? Drop your guess below before we go further. You may be surprised by where we land. On number 3, the border at the bottom of forever, the edge where falling becomes eternal. Before we can talk about what is at the center, we have to talk about the road in. Because the road to the center of a black hole is unlike any other road in the universe. It does not pass through ordinary distance. It does not move forward in ordinary time. It has a beginning in the sense that you can choose to step onto it, but it has no exit, no fork, no shoulder, no off-ramp. Once you are on it, the road keeps unfolding in front of you and behind you in a way that nothing in your ordinary life has prepared you for. The doorway to that road is called the event horizon. It is the surface that defines a black hole as a black hole. It is not a wall. It is not made of anything. There is no plaque to read, no sign to warn you, no detector that would tell you the moment you crossed it. The event horizon is simply a mathematical surface around a sufficiently dense object, a surface beyond which the curvature of spacetime is so steep that every possible path forward, every direction you could conceivably travel, no longer points outward. Every direction, every choice, every wiggle of your body, every motion of every particle in your hand, all of them now point toward the center. Let that settle for a moment. Below the event horizon, the center of the black hole is no longer a place. It is a time. It is your future. You cannot avoid it any more than you can avoid tomorrow. You cannot turn around and head back, because back is no longer a direction that exists. The geometry has tilted so far that what we ordinarily call space and what we ordinarily call time have swapped roles. The radius, the distance from the center, has become a time-like coordinate. Time, in the ordinary sense, has become a space-like one. You can move sideways. You can rotate. You can throw your arms out and look at your hands. But you cannot stop falling, because falling is no longer a direction. Falling is the next moment. If you are sitting somewhere quiet right now, perhaps in a dim room, perhaps with your eyes closed, try to feel that for just a heartbeat. The future for you is the next minute, the next breath, the next thought. The future is something that arrives whether you wish it or not. Now imagine that the future, for someone who has crossed the event horizon, is not a moment but a place. The center, the singularity, the wherever it is at the bottom, is what their future literally consists of. They are moving toward it not by choice but by the same force that drives you, here in your dim room, into the next second of your own life. They cannot rebel against the geometry any more than you can rebel against time. And yet, and this is the part that almost no one mentions, the crossing itself, the moment you pass through the event horizon, is unremarkable. There is no shock. There is no sound. There is no flash of light. For a black hole large enough, the tidal forces at the horizon are gentle, almost tender. You could fall through the horizon of a supermassive black hole, like Sagittarius A star at the center of our galaxy, without noticing the moment of crossing at all. The doorway is invisible. The transition is silent. You only realize much later that the universe outside is no longer reachable, because the light from your own body, if you tried to send it backward, would simply not be able to climb the slope you have already slid down. This is what physicists mean when they say a black hole has no surface. The event horizon is not a thing. It is a one-way membrane in the geometry of spacetime. From the outside, it looks like a sphere, but from the inside, it does not look like anything. It is everywhere behind you, but you cannot turn around to see it. Some physicists have described this with a beautiful and unsettling image. From inside a black hole, the entire universe outside, every star, every galaxy, every photon ever emitted by anything you have ever seen, is compressed into a single bright spot above you, dimming and blue-shifting, as you fall and finally vanishing into a singular point that contains all of the cosmos you have left behind. Below you, in the direction you are falling, there is only darkness, and the geometry of that darkness is not the geometry of ordinary space. Now here is the part that breaks most people's intuition. There are two different kinds of black holes when it comes to the road inward, and they are not at all the same. There is the Schwarzschild black hole, the simple, idealized, non-spinning, non-charged kind, which is what the original equation gave us a century ago. And there is the Kerr black hole, named for the New Zealand mathematician Roy Kerr, who in 1963 found a solution to Einstein's equations for a spinning mass. The Kerr solution is what real black holes resemble, because every black hole we have ever observed spins, sometimes incredibly fast. Sagittarius A star is rotating. M87's giant black hole is rotating. The collisions LIGO has heard are between spinning black holes, dancing together at near the speed of light. And the inside of a spinning black hole, the Kerr black hole, is profoundly different from the inside of the idealized one. A Schwarzschild black hole, the non-spinning kind, has a single singularity at the center, a point. A Kerr black hole, the spinning kind, does not. A Kerr black hole has, instead, a singularity that is shaped like a ring. A flat circle, a one-dimensional loop, lying in the equatorial plane of the spin. And around that ring, the geometry of spacetime is so strange that physicists, when they first calculated it, refused to believe it was real. They thought there must be a mistake. The equations seem to say that if you fell in along the spin axis, missing the ring, you could in principle pass through the center and emerge into another region of spacetime entirely. A region that was not the universe you came from. A region with its own past and its own future. The equation suggested, in other words, that the interior of a Kerr black hole might contain other universes. Plural. An infinite ladder of them, stacked beyond the singularity in a structure no human mind can really picture. For decades, this was treated as a mathematical curiosity, a solution that worked on paper but could not possibly correspond to anything real, and it may well not. The internal structure of an actual, formed black hole is almost certainly not the eternal, idealized Kerr solution. Real black holes form from collapsing stars. They are not pre-existing. Their interiors are scarred by infalling matter, by the radiation of the early universe, by the energy of whatever it was that fell in. The simple Kerr solution does not survive contact with reality. But the strangeness of what it suggested, the hint that the center might not be a single point but a doorway, has never quite gone away. It lurks, it whispers, and we will come back to it before this night is done. For now, though, let me ask you. If you could, hypothetically, fall through the horizon of an enormous black hole, knowing you would not feel the crossing, knowing the journey inward might last hours or days depending on the size, knowing you would never return, would you do it? Would the chance to see what no one has ever seen be worth the certainty of not coming back? Tell me below. There is no wrong answer. But the answer you give might tell you something about how much wonder is worth to you and how much of it you have left. On number 4, when the body becomes a memory, the stretching of matter into light. Let us be honest about what would happen to you if you actually fell. Because the popular picture of falling into a black hole, the picture of a spaceship being torn apart by the gravity, the picture of a person stretched into a noodle, is partially right and partially wrong, and the truth is more nuanced and more terrible than either. The technical term, used by physicists with a rare flash of humor, is spaghettification. It is the word coined to describe what happens to an object falling into a region of severely non-uniform gravity. The body of any extended object, your body, a satellite, a planet, a star, is held together by chemical and gravitational bonds that are, in everyday life, vastly stronger than the difference in gravity from one end of the object to the other. You do not stretch when you stand up, even though your head is in slightly weaker gravity than your feet, because the difference is negligible and your tissues are firm. Near a black hole, that ceases to be true. The gradient of gravity, the difference in pull between 2 points only a meter apart, can become so steep that the bonds holding your body together can no longer fight it. Your feet, if you fell in feet first, would be pulled toward the center with measurably greater force than your head. You would stretch, slowly at first, then faster. Eventually, your body would be drawn out into a thin, lengthening filament, like dough pulled by a baker, and the filament itself would continue to thin, atom by atom, until the structure of matter as you know it would no longer hold. But here is the surprising part. For a small black hole, a stellar mass black hole formed from the death of a single sun, this spaghettification begins outside the event horizon. Far outside. You would never get the chance to cross the horizon as a whole human being. You would be torn apart in the swirling gases above it, your atoms scattered into the accretion disk, long before you saw the darkness up close. The smaller the black hole, the more vicious the gradient at the horizon, because the horizon is closer to the central concentration of mass. A small black hole has a curved nose, sharply curved, and it shreds you on approach. A large black hole, paradoxically, is far gentler. The supermassive black holes at the centers of galaxies, the ones with millions or billions of times the mass of our Sun, have event horizons so vast, so smoothly curved, that the gradient of gravity across the body of a falling human is almost imperceptible at the moment of crossing. You could pass through the event horizon of Sagittarius A star, a black hole some 4 million times the mass of the Sun, without any sensation of stretching at all. The horizon there is enormous, larger than the orbit of Mercury. The curvature is broad. The tides are gentle. You would notice, perhaps, a strange thickening of light around you, a distortion in how the stars overhead appeared, but the crossing itself would be eerily uneventful. The spaghettification would still come, but it would come later, deeper. As you fell toward the center, the curvature would steepen. The gradient would sharpen. Eventually, somewhere on the long road inward, the tides would rise to a point where your body would begin to tear. And then, very quickly, the tearing would accelerate, because the closer you got to whatever was at the bottom, the more sharply the gravity changed across each remaining millimeter of you. In the last fraction of a second of your existence as a coherent body, you would be drawn out into a stream of particles, and then those particles would themselves be drawn out, and then their components, and then whatever components those might have, until finally everything that had ever been you was a single thin line of radiation falling forever inward. There is a strange and almost sacred image hidden in this. Whatever you were, whatever you carried with you, whatever histories your atoms had accumulated over their long lives in stars and in clouds, and in the air of your home planet, all of those would be unspooled. The patterns that made you you, the configurations of molecules that held a memory, an idea, a face you loved, all of them would be combed apart. And the question of what happens to those patterns, what happens to the information that you contained, is one of the deepest questions in modern physics. It is so deep that it has had a name for decades: the information paradox. We will return to it before the night is through, because it is the heart of why the center of a black hole is such a profound mystery. The information has to go somewhere. The math demands it. But where it goes, and how it gets there, may force us to rewrite the very definition of a black hole's interior. For now, though, take a moment with what we have just walked through. The crossing of the horizon, the slow steepening of the tides, the unraveling of the body into a line. There is no escape from this once it begins. And yet, if there is any consolation, it is that, for a large enough black hole, you would experience much of the journey as if you were still whole, still thinking, still falling through what looked, to your own eyes, like ordinary space. The disintegration would come quickly at the very end, but the descent, the long descent through curved geometry, would be eerily calm. So let me ask you, if you knew you had only an hour left, falling through a vast black hole, never to return, how would you spend that hour? Would you look back at the universe behind you, watching the stars compress into a single bright spot above? Would you turn inward and think? Would you talk to whoever was with you until the words ran out? It is a strange question, but it touches on something real about how human beings face the unstoppable. Share what you would do below. We are about to descend into the deepest part of the mystery, and a moment to think about your own answer to that question may make what comes next hit a little harder. On number 5, the crash at the bottom of mathematics, where equations politely excuse themselves. So we have crossed the horizon. We have felt the geometry tilt, the future fold into a direction we cannot resist. We have stretched, we have unraveled, we have ridden the descent through curving spacetime. And now we are approaching the center. The place that in every textbook diagram you have ever seen is marked as a single point, a small black dot, a label that reads in clean letters singularity. And here is where physics begins, very quietly, to fall apart. The singularity, as predicted by general relativity, is a point of infinite density, or in the case of a spinning Kerr black hole, a ring of infinite density. It is a place where the curvature of spacetime becomes infinite, where the gravitational tidal forces become infinite, where the volume of any region around it shrinks to zero. Every quantity in Einstein's equations, every well-behaved mathematical object that we use to describe the universe, goes to infinity at the singularity. And in physics, infinity is not a result. Infinity is a flag. Infinity is the equation telling you that the assumptions you started with have broken. To understand why this is such a deep problem, you have to understand a peculiar fact about the history of science. Whenever, over the past several centuries, our best theories have predicted infinities, those infinities have always turned out to be a sign that the theory was incomplete. Always. There is no exception in the modern record. The infinities of pre-quantum atomic physics, where electrons should have radiated all their energy away and collapsed into the nucleus in a flash, were resolved by the invention of quantum mechanics. The infinities of classical electrodynamics, where the self-energy of a point charge was infinite, were tamed by quantum field theory. The infinities of the Big Bang, where every modern cosmology textbook places a starting singularity, are widely suspected to be the product of our incomplete description of the very early universe. Whenever the math breaks, history tells us, the math is the problem, not the universe. The singularity at the center of a black hole is the most violent infinity in modern physics. It is not a small irregularity. It is total. Curvature goes to infinity. Density goes to infinity. The energy required to compress an object to the singularity's size goes to infinity. The future light cone of every observer inside the horizon, every direction they could conceivably travel, terminates at the singularity in finite time. There is no escape from it within the geometry of general relativity itself. And yet, by every historical lesson we have learned, that prediction cannot be the final word. There must be something else, something that takes over when the curvature becomes too extreme for Einstein's equations to handle. What is that something else? The honest answer is that we do not know. We have a name for it. We call it quantum gravity. It is the theory we have been trying to build for nearly a century, the theory that would combine general relativity, our description of gravity and spacetime, with quantum mechanics, our description of matter and energy at the smallest scales. These two theories are the twin foundations of modern physics. Together, they explain almost everything we have ever measured, and yet they refuse to merge. They are written in different mathematical languages. They assume different things about the nature of reality. General relativity treats spacetime as smooth and continuous. Quantum mechanics suggests that everything at small enough scales is grainy, probabilistic, uncertain. Where these two theories meet, in the screaming center of a black hole, in the first moments after the Big Bang, in the foam at the smallest possible distances, neither of them is fully trustworthy. And we have not yet built the bridge. The scale at which this matters is unimaginably small. It is called the Planck scale, named for Max Planck, the father of quantum theory. The Planck length is about 10 to the minus 35 meters. To give you a sense of how small that is, if an atom were the size of our entire solar system, the Planck length would still be smaller than a single hydrogen atom inside that solar system-sized atom. It is the scale at which space itself is suspected to lose its meaning as a smooth continuum and begin to behave in some quantum, foamy, grainy way that we do not yet understand. The singularity at the center of a black hole, according to general relativity, is far smaller than the Planck length. It is, in fact, zero in size, and at that scale our equations are not just imperfect, they are blind. So when a physicist tells you there is a singularity at the center of a black hole, what they are really telling you is this. According to our best classical theory, the curvature there goes to infinity. But we know our classical theory is wrong at that scale. We know it because the singularity is exactly the kind of result that history tells us means a theory has broken. We know it because any sane physicist treats infinity in an equation as a warning rather than a destination. And we know it because, when we try to combine our theory of gravity with our theory of quantum mechanics, we get answers that are not infinity. We get answers that are strange and finite and totally different from the classical prediction. We just do not yet know which of those answers is right. This is where the story really begins. The center of a black hole in the actual physics of the present day is not a known quantity. It is a place where multiple theories make competing predictions. Some predict a tiny but finite core of incredibly dense matter. Some predict a region of space that behaves more like a quantum foam than like anything we would call substance. Some predict a portal, a bounce, a tunnel into something else. Some predict that the very concept of an interior is wrong, that there is no inside at all, only a surface that contains all the information of what fell in. Each of these is a real proposal, made by real physicists, drawn from real mathematics. And we are about to descend through them, one by one, like floors of a building whose architecture we do not yet fully understand. Let me ask you something now, before we go on. When you hear that some of the deepest questions in physics are still unanswered, that there are real disagreements among the smartest people who have ever lived about what happens at the heart of an object we have photographed twice, does that make you feel uncertain? Or does it make you feel hopeful? Because mystery, real mystery, is one of the great gifts the universe still offers us. There is still room, in the year you are listening to this, for a curious mind to look up at the sky and ask a question no one has answered. And every layer we descend from here is going to be more honest about that than the last. Tell me below whether mystery comforts you or unsettles you, and then we will keep going. On number 6, the stalled heart of a dying sun, how a star folds itself into darkness. To know what is at the center of a black hole it helps to know how the center got there. Because the singularity, or whatever object lives in its place, is not some pre-existing feature of the universe. It is the end state of a process. A long, slow, almost reluctant process of cosmic collapse. And the story of that collapse is the story of how matter loses, one by one, every defense it has ever developed against gravity. Consider an ordinary star, our sun, for instance. The sun is a sphere of plasma about 1 million miles across, holding itself up against its own colossal weight by the heat of nuclear fusion in its core. Every second, inside the sun, hundreds of millions of tons of hydrogen are crushed into helium, releasing the energy that makes the star shine, and that pushes outward against the inward crush of gravity. This balance, this delicate equilibrium between outward pressure and inward weight, is what we call hydrostatic equilibrium. It is the reason the sun has been the size it is for about 4.5 billion years. Push and pull, fire and weight, in eternal stalemate. As long as the fuel lasts, but the fuel does not last forever. Eventually, every star runs through its hydrogen. The sun, in about 5 billion years, will exhaust the hydrogen in its core and begin to burn helium, swelling into a red giant, and then shedding its outer layers, leaving behind a small, hot, dense core called a white dwarf. The white dwarf is held up not by fusion, which has ceased, but by something called electron degeneracy pressure. This is a quantum mechanical effect. Electrons, by the laws of the very small, cannot all occupy the same state. They resist being squeezed together. They push back. And that resistance, that subtle quantum reluctance, is enough to hold up an object as massive as our sun, compressed into a sphere about the size of the Earth. Bigger stars cannot stop there. Stars several times the mass of the sun, when they exhaust their nuclear fuel, collapse under their own weight so violently that electron degeneracy pressure cannot save them. The electrons get crushed into the protons inside their atoms, fusing them into neutrons in a flash of energy, releasing a torrent of neutrinos that blows away the outer layers of the star in a supernova explosion. What remains is a neutron star. A ball of pure neutrons, about a dozen miles across, weighing more than the sun. The density there is staggering. A sugar cube of neutron star material would weigh, on Earth, about 1 billion tons. The surface gravity is so intense that the entire star would fit on the island of Manhattan, with room to spare for the bridges. But it does not collapse further, because neutrons, like electrons, also resist being crammed together. Neutron degeneracy pressure holds the star up against its own weight, and the balance is restored. But there is a limit, even to that. Above a certain mass, somewhere around 2 to 3 times the mass of the sun, even neutron degeneracy pressure fails. The star collapses past the threshold of any known physics. The neutrons themselves are crushed into something we do not have a name for. The collapse, having defeated every kind of outward push that matter knows how to generate, simply runs away. The star falls into itself, faster and faster. The surface, the bright skin of the dying star, plunges inward at a significant fraction of the speed of light. The gravity at the center grows, the curvature of spacetime around the collapsing matter steepens, and at some point the geometry forms a closed surface around the doomed star. An event horizon. From the outside, the star appears to freeze at the horizon, redshifting and dimming forever, its light stretched into longer and longer wavelengths until it fades into invisibility. From the inside, the collapse continues. There is no stopping it. There is no equilibrium left to find. The matter falls and falls and falls, and according to general relativity, in a finite amount of time, all of it arrives at the same place, the center. That arrival is what the equations call a singularity. Every particle, every atom, every neutron and electron that was once the heart of a dying star, gathered at a single point of zero size and infinite density. It is the logical conclusion of unstoppable collapse. It is what the math demands. And it is, as we have already discussed, almost certainly not what actually happens. Because at some point during that descent, before the matter reaches zero size, the density becomes so high that quantum mechanical effects must take over. The Planck scale must intervene. The smooth geometry of Einstein's equations must give way to whatever the deeper theory turns out to be. And what happens then is not a single answer but a family of possibilities, each one with its own advocates, its own equations, its own beautiful and unsettling implications. This is the moment when we leave the comfortable territory of established physics and step into the contested ground of modern theoretical work. Different physicists, working with different versions of quantum gravity, have written down different possibilities for what waits in the deep interior of a black hole. None of these possibilities has been observed. None has been ruled out. All of them are, in principle, consistent with everything we know. And the disagreement among physicists, far from being a sign of failure, is actually a sign of how lively this question still is. Because the singularity at the center of a black hole is not a closed book. It is one of the most active and exciting research questions in fundamental physics, and the answer, when it finally comes, is going to reshape our understanding of what reality is made of. So let me ask you, when you imagine the death of a star, the slow stalling of its fusion, the catastrophic implosion of its core, the formation of something that bends light into a circle and traps it forever, do you feel sadness or awe or something else? Because the universe makes black holes the way a forest makes fallen leaves. They are everywhere. Our galaxy alone is estimated to contain at least 100 million stellar mass black holes. And every single one of them began as a star, just like our sun, that lived and burned and finally fell into itself. There is something almost mournful about that, and something almost beautiful. Tell me which one you feel more strongly, sadness or awe, when you picture it. We will hold that feeling as we descend further. On number 7, the trapped light in the sealed throat, what an outside observer cannot find out. Before we plunge into the various competing theories of what the interior actually contains, we need to slow down and confront something that is often glossed over. The fact that every theory we are about to discuss is, in a profoundly important sense, untestable. Or at least, untestable in any straightforward way. Because the defining property of a black hole, the one feature that gives it its name, is that nothing inside its event horizon can send a signal out. This is not a technical limitation. It is not a problem of building a better telescope. It is a structural property of the geometry. Light, the messenger that carries almost all the information we have ever received from the cosmos, is bound by the curvature of spacetime just as surely as you are. Inside the horizon, every possible path that light could take points inward. There is no path that points outward. There is no trajectory that climbs the slope. Light cannot escape, not because something is holding it down, but because outward is no longer a direction that exists. This is why the photograph the Event Horizon Telescope took of M87 and the photograph it took of Sagittarius A star both show a dark disk surrounded by a ring of light. The ring is the last light that managed to climb out of the steep gravitational well, bent into orbits by the curvature near the horizon. The dark disk is the shadow of the black hole. Inside that shadow, no light emerges. No information arrives. The photograph is, in a real sense, a portrait of an absence. It is the universe's way of saying, here is where my speech ends. And yet, despite this, we are not totally helpless. There are indirect ways to probe the interior. There are signatures we can look for in the radiation emitted from the very outermost edge of the horizon. Signatures that might differ depending on what kind of internal structure the black hole has. There are gravitational wave signals from merging black holes that, in their last few milliseconds, might carry subtle echoes of what is happening just inside. There are theoretical consistency arguments, where physicists ask whether a proposed interior structure is compatible with everything else we know about quantum mechanics and gravity, and rule out the ones that fail. In recent years, especially since the deployment of LIGO and the Virgo detector, scientists have begun looking for what are called gravitational wave echoes. The idea is that if a black hole has some kind of structure just inside the horizon, some kind of solid surface or quantum membrane or sudden change in geometry, then gravitational waves emitted during a merger might bounce off that surface and arrive at our detectors slightly after the main signal. A delayed ripple, a faint repeat. As of right now, no clear evidence of such echoes has been confirmed. The mergers we have observed look to within our current sensitivity, like classical black holes with smooth horizons and no interior surface. But the searches continue, and future detectors, like the planned Einstein telescope and the space-based LISA observatory, will be far more sensitive than what we have today. There is another tool, far less direct but equally important, called the Event Horizon Telescope, the same array of radio dishes that took the photographs. By looking very carefully at the shape of the shadow, the size of the ring, and the polarization of the light around it, the EHT team has been able to test whether real black holes match the predictions of general relativity to a remarkable degree of precision. So far, everything they have measured is consistent with the classical Einstein prediction. The shape of the shadow matches what a Kerr black hole should look like. The size of the ring agrees, within measurement error, with what relativity predicts for an object of the measured mass. The polarization patterns reveal organized magnetic fields spiraling at the edge of Sagittarius A star, which themselves match the patterns previously seen at the edge of M87, suggesting that strong, structured magnetic fields are a common feature of black holes. None of this directly tells us what is inside. But it does tell us that, at least at the level of the horizon and the regions just outside it, real black holes are behaving exactly as Einstein's equations predicted, with no surprises so far. This is both reassuring and frustrating. Reassuring because it means our basic picture of black holes, that they are real, that they obey general relativity, that they have an event horizon and a shadow and a region of trapped light, is on extremely solid ground. Frustrating because it means we have no direct empirical window into what lies inside. The interior remains theoretical. The interior remains, in some real sense, hidden behind a veil that physics itself has woven, a veil we may never be able to lift. But this is also part of what makes the question so beautiful. Because the inside of a black hole is the only place in the entire observable universe that we can never observe. Every other region of space, no matter how distant, no matter how faint, is in principle reachable by light. We could, given enough patience and the right instruments, see anywhere in the cosmos that is causally connected to us, except the inside of a black hole. The inside of a black hole is the universe's only true secret, the only place where the cosmos refuses to show its hand. And the questions we ask about it, the theories we build, the models we test, are a kind of conversation with that silence. A way of trying to coax meaning out of a place that refuses, by its very geometry, to answer back. So tell me, does it bother you that there exists a region of the real universe that is permanently inaccessible to direct observation? Or does the existence of such a place make the universe feel deeper, richer, more worth exploring? Some people find the inaccessibility maddening. Some people find it sacred. There is no right answer. But the next several layers we are going to explore are humanity's best attempts to peek through the veil anyway, and they get stranger and stranger as we go. So get comfortable. We are about to walk through the 4 leading theories of what actually exists at the bottom of the well. On number 8, the fire at the edge, the wall that might burn you alive. Let us start with the strangest of the modern proposals, the one that scared a lot of physicists into rethinking the foundations of their field. It is called the firewall, and the firewall, if it exists, is not at the center of the black hole at all. It is at the surface, at the event horizon. It is a wall of unimaginable energy, an inferno of high-energy particles, lying right at the threshold of the black hole and ready to incinerate anything that crosses it. The firewall proposal was published in 2012 by four physicists named Almary, Maroff, Polchinski, and Sully. Their names get bundled together in the abbreviation AMPS, and the firewall is sometimes called the AMPS paradox, because what they were really proposing was not so much a definite feature of black holes as a problem with our existing understanding. The argument went something like this. According to general relativity, the event horizon of a sufficiently large black hole should be unremarkable. There should be nothing special at the horizon itself. An observer falling through it should feel no shock, no temperature change, no warning of any kind. The horizon is, locally, just empty space. The principle that says this is sometimes called the equivalence principle, and it is one of the foundational ideas of Einstein's theory. It says that you cannot tell, locally, whether you are in a gravitational field or in free fall. Free fall through a horizon should feel just like free fall anywhere else. According to quantum mechanics, however, certain things have to be true about the radiation a black hole emits. As Stephen Hawking discovered in 1974, black holes are not entirely black. They glow very faintly, with a thermal radiation now called Hawking radiation. The radiation is emitted from just outside the horizon, and over enormous timescales, much longer than the current age of the universe for any black hole bigger than a small asteroid. The black hole gradually loses mass to this glow. Eventually, in the very distant future, a black hole could evaporate completely, releasing all of its mass energy back into the cosmos as a long, slow trickle of radiation. For decades, this raised a question. Where does the information go? The matter that fell into the black hole carried information. Quantum mechanics says information cannot be destroyed. And yet Hawking's calculation showed that the radiation coming out is thermal, random, featureless, carrying no clear imprint of what fell in. If the black hole eventually evaporates and the radiation is truly random, then the information has vanished. And the destruction of information is, in a sense, more troubling than the destruction of matter. It violates one of the most cherished principles in physics. For a long time, physicists hoped that the information might be encoded subtly in the Hawking radiation, in correlations between particles emitted at different times. This is the famous Page curve we have come to know in recent years, after the physicist Don Page, who first computed how the entanglement of the radiation should evolve if information were preserved. And in recent calculations, especially since 2019, several teams have shown that, when you do the math carefully, the Page curve does emerge. Information does seem to come out of the black hole. The evaporation is unitary, meaning it preserves the total information content of the universe. This was a landmark result. It seemed to resolve the paradox, but here is where AMPS struck. They pointed out that if information escapes via Hawking radiation, then late emitted radiation must be entangled with earlier emitted radiation in a very specific way. And by another principle of quantum mechanics, no particle can be maximally entangled with more than one other system. This is sometimes called monogamy of entanglement. It means that if a Hawking particle is entangled with earlier outgoing radiation, it cannot also be entangled with its infalling partner across the horizon, as the original Hawking calculation required. And that creates a problem. Because if the entanglement between the infalling and outgoing partners is broken, then crossing the horizon is no longer smooth. The local equivalence principle breaks. There is suddenly a discontinuity in the quantum field right at the horizon, and the energy required to break that entanglement is enormous. It would manifest as a sheet of high-energy particles, a wall of fire, a literal inferno at the surface of the black hole, so the AMPS authors presented this as a choice. Either we abandon the equivalence principle and accept that the horizon is a wall of fire that burns infalling matter to a crisp, or we abandon the preservation of information and accept that black holes destroy information after all. Or we abandon some other deeply held principle of physics that we have not yet identified. For more than a decade now, physicists have been wrestling with the firewall paradox. Some have proposed that it can be resolved by accepting a kind of complementarity, where what an outside observer sees and what an infalling observer experiences are simply different and equally valid descriptions of the same physics. Some have proposed that the firewall is real, that the horizon really is a wall of fire, and that the smoothness of crossing predicted by Einstein is an illusion that breaks down at the quantum level. Some have proposed solutions involving wormholes, hidden geometric connections, what Maldacena and Susskind called ER equals EPR, the conjecture that entanglement and tiny wormhole connections might be the same underlying phenomenon. There is no consensus. The argument is alive. And the implications, if the firewall turns out to be real, would utterly change our picture of what crossing a black hole even means. If the firewall exists, then the smooth descent we described earlier, the calm crossing of a supermassive black hole's horizon, would not happen. Instead, you would be vaporized at the threshold, reduced to particles, annihilated by a sheet of pure energy that lives precisely where the horizon should be smooth and quiet. The interior, the question of what is at the center, would be unreachable not because of distance, but because nothing that crosses the horizon survives as a coherent observer. The firewall would burn you before you ever saw what was inside. But you might be wondering, even if the firewall exists, what is at the center? Because the firewall is a feature of the surface, not the interior. And the answer, even if you accept the firewall picture, is that we still do not know. The firewall makes the interior harder to even talk about because nothing intact gets there. But the question of what would be inside if anything could survive the crossing remains open. And so we keep falling. So let me ask you, does the idea of a wall of fire at the boundary of every black hole change how you think about them? Does it make them more frightening or just more strange? Are you more drawn to a picture where the universe is calm and continuous, with smooth horizons and gentle crossings, or to a picture where it is full of hidden walls and sudden transitions that defy our intuition? Tell me which version of nature feels truer to you. The disagreement is real, even among the experts, and your gut, in this case, is as good a starting place as any equation. On number 9, the knotted strings at the bottom, when matter becomes a music, let us move to a second proposal. A more radical one, in some ways. A picture in which the singularity does not exist at all, not because something replaces it, but because the entire interior of the black hole is filled with a strange kind of stuff that physics had never quite imagined before. This is the Fuzzball proposal, and the Fuzzball, if it is correct, would mean that the inside of a black hole is not a void surrounding a singular point. It is not empty space at all. It is a dense, structured, exotic substance that fills the entire interior, all the way out to the horizon. The fuzzball idea comes from string theory. String theory, you may have heard, is one of the leading candidate theories for unifying gravity with quantum mechanics. Its core claim is that the most fundamental things in the universe are not point particles, but tiny vibrating loops, called strings, whose different modes of vibration correspond to the different particles we observe. An electron is a string vibrating one way. A photon is a string vibrating another way. The graviton, the hypothesized particle of gravity, is yet another mode, and the strings are unimaginably small, near the Planck scale, which is why they appear point-like in every experiment we have ever done. String theory has been controversial for decades, partly because it has been difficult to derive testable predictions from it, and partly because it requires extra dimensions of space that we do not directly observe. But it has produced some genuinely interesting mathematics, and one of its more famous applications, developed beginning in the late 1990s by the physicist Samir Mathur and others, is the proposal that black holes, when properly understood within string theory, do not have singular centers. They have fuzzballs. Here is the idea. In ordinary general relativity, a black hole is described by very few numbers: its mass, its electric charge, and its spin. That is it. Any two black holes with the same mass, charge, and spin are classically identical. They have no distinguishing features. This is sometimes called the no-hair theorem, the idea that a black hole has no hair, meaning no detailed structure. But this presents a deep problem, because the matter that fell into a black hole had enormous amounts of information. Vast numbers of particles, each in some quantum state, contributing to the black hole's total content. If a black hole is described by only 3 numbers, where did all that information go? The Fuzzball proposal says the information did not go anywhere. It is still there. It is encoded in the detailed quantum state of the black hole's interior. And the interior, in the Fuzzball picture, is not a smooth, empty volume containing a point singularity at its center. It is a richly structured tangle of strings and higher-dimensional objects, called branes, that fills the entire region inside what we would normally call the horizon. The fuzzball does not have a sharp surface. Its surface is exactly where, classically, the horizon would be. But there is no horizon in the ordinary sense, because the fuzzball is solid all the way through. It is, in some sense, a giant elementary particle with its own internal structure, masquerading as a black hole. If the fuzzball picture is right, then the answer to the question what is at the center of a black hole becomes very strange. There is no center in the sense of a special point. There is no singularity. The interior is uniformly filled with stringy structure, and the question of what is at the center is no more meaningful than asking what is at the center of a marble. The marble is full of marble all the way through. The fuzzball is full of fuzzball all the way through, and the apparent featurelessness of the black hole, the no-hair, is just a coarse-grained illusion. Up close, every black hole is unique, with a distinctive quantum signature determined by the precise history of what fell in. This proposal has some elegant features. It resolves the information paradox in a natural way, because the information was never inside an inaccessible region. It was always part of the fuzzball's quantum state, encoded right where the matter ended up. It gives black holes a kind of microstructure that brings them in line with all the other quantum objects we know. And it eliminates the singularity entirely, because the interior is filled with a finite density, finite curvature configuration of strings, never reaching the infinite values that plague general relativity. It also has some serious challenges. The mathematics of fuzzballs is extremely difficult, and explicit fuzzball solutions have only been constructed for special, highly symmetric, idealized black holes. Whether real, astrophysical black holes, with all their messiness and asymmetry, can also be described as fuzzballs is an open question. And the proposal makes predictions that are, in principle, distinguishable from classical black holes, but only in regimes that are extremely difficult to observe. The current photographs from the Event Horizon Telescope and the gravitational wave signals from LIGO are consistent with both classical black holes and fuzzballs because they cannot yet resolve the differences. Future detectors, more sensitive ones, may be able to. But for now, the fuzzball remains a beautiful theoretical possibility, neither proven nor ruled out. And what is so haunting about the fuzzball picture, when you sit with it for a while, is its suggestion that what we have been calling empty space inside a black hole is not empty at all. It is full. It is humming with structure. It is alive with the residue of every star and every cloud and every particle that ever fell in, all of them woven into a tapestry of strings whose pattern is unique to each black hole. The center of a black hole in this picture is not a void. It is a memory, a vast, almost incomprehensibly detailed memory of everything that ever entered. So let me ask you, does that idea that the inside of a black hole might be full rather than empty change anything for you? Most of us growing up with the funnel picture imagine the inside as a void, a hollow space leading to a tiny point. The fuzzball asks us to flip that, to picture the inside as densely filled, like a star or a planet but stranger, with all the matter that ever fell in still present in some form, contributing to the texture of the whole. Does that feel more comforting somehow, or more alien? Tell me what comes up. There is no wrong way to react, and we are about to descend even further into a third possibility that is, in its own way, even stranger. On number 10, the surface that holds the inside, the whisper that reality may be a hologram. Now we come to one of the most beautiful and bewildering ideas in modern physics. An idea that, if it turns out to be correct, would not just change how we understand black holes, it would change how we understand the universe. The idea is called the holographic principle. And it says in its boldest form that the inside of a black hole, and perhaps the inside of any region of space, is not separate from its surface. The interior is, in a deep mathematical sense, encoded on the boundary, like a hologram. The three-dimensional content is fully captured by the two-dimensional surface that surrounds it. This idea did not come from someone playing with metaphors. It came from a very specific and surprising mathematical discovery made in the 1970s by Jacob Bekenstein and Stephen Hawking. They were studying the thermodynamics of black holes, trying to understand how concepts like entropy, the measure of disorder in a system, applied to objects that were supposed to be featureless. And what they found was strange. The entropy of a black hole, they showed, was not proportional to its volume, as the entropy of ordinary objects is. The entropy of a black hole was proportional to the area of its horizon. The amount of disorder, the amount of information content, scaled with the surface, not with the inside. This was deeply weird. In every other physical system you can think of, entropy is an extensive quantity. Double the volume, double the entropy. A cup of water has twice the entropy of half a cup of water, but a black hole has entropy proportional to its surface, not its volume. Make the black hole bigger by some factor, and its entropy grows not as the cube of that factor, as you would expect from a three-dimensional object, but as the square. As if the relevant degrees of freedom, the bits of information, were not living in the volume at all. As if they were living on the surface. In the 1990s, physicists like Gerard Hooft and Leonard Susskind took this observation and ran with it. They proposed what came to be called the holographic principle. The idea that the maximum amount of information you can pack into any region of space is proportional to the area of the boundary of that region, not its volume. And from this, they suggested something even more radical. That the physics inside any region of space might be equivalent to a description of the physics on its boundary. The interior, in this view, is a kind of holographic projection of information that lives on the surface. In 1997, the Argentine physicist Juan Maldacena made this idea concrete in a specific mathematical context. He showed that a particular kind of theory of gravity in a five-dimensional curved spacetime is exactly equivalent to a particular kind of quantum theory living on the four-dimensional boundary of that spacetime. This is sometimes called ad-SCFT correspondence, and it is one of the most influential discoveries in theoretical physics over the past several decades. It gave physicists a concrete example in a particular toy universe where the holographic principle was demonstrably true. The interior of that toy universe was mathematically the same as a quantum theory on its surface. Now apply this to a black hole. If the holographic principle is correct, then everything inside a black hole, every detail of every particle, every quantum state, every speck of information about what fell in, is encoded on the surface of the horizon. The interior is not really separate. It is a different way of describing the same content that lives on the boundary. And in this picture, the question of what is at the center of a black hole becomes profoundly strange, because there may not be an inside in the usual sense. The inside may be a kind of illusion, a different language for the information stored on the surface. This is hard to picture, almost impossibly hard, because we live in a world where insides feel obviously different from outsides. The inside of your room is a different place than the outside. You can be in one or the other, but not both. And the holographic principle is saying, in effect, that this common-sense distinction breaks down at a deep enough level. That insides and outsides are dual descriptions, not separate realms. That every interior is somehow a complicated story told on its own boundary. If this is right, then what is at the center of a black hole? In a sense, nothing. In a sense, everything. The center is not a different place than the surface. The center is the same content, viewed from a different mathematical angle. The information that you might naively think is sitting at the bottom of the gravitational well is actually distributed across the horizon, encoded in a way that is mostly invisible to outside observation but, in principle, fully present. And here is the part that has been driving theoretical physics over the past several years. The same page curve calculations that showed information escapes black holes, the ones that won partial credit for resolving the information paradox, were performed using exactly this kind of holographic reasoning. The successful calculations relied on a concept called quantum extremal surfaces, geometric structures inside the black hole that capture how the interior is entangled with the exterior. And those calculations strongly suggest that the holographic picture is, in some form, correct. That the inside of a black hole is not a separate region of reality but a deeply entangled extension of the surface, and that the information stored there is recoverable, in principle, from observations made far away. Take a breath with me here. Because what we are describing is a vision of reality where the inside of a black hole is, in some genuine mathematical sense, a hologram, a projection, a pattern in the surface dressed up to look like a volume. And by some readings of the holographic principle, this might not be a special feature of black holes. It might be a feature of all of space. Everything we see, everything you have ever touched, every star, every galaxy, every thought in your own head might be a holographic projection of information that lives somehow on a boundary of the universe. The cosmos in this picture is not what it looks like. It is a kind of vast, structured illusion, and the appearance of three-dimensional depth is a way of organizing information that fundamentally lives in a layer. This is far from settled science. The holographic principle in its most general form is a conjecture, not a proven fact. The specific version Maldacena worked out, ad SCFT, has been tested in many ways within its mathematical context, but our universe is not that particular kind of toy universe. Whether real black holes in real spacetime are exactly described by holography is an open question. But it is one of the most actively pursued questions in physics, and the evidence so far has been quietly accumulating in its favor. So let me ask you, if reality, including you, including the room you are in, including the stars overhead, were in some deep sense a holographic projection of information from a boundary you cannot directly see, would you feel diminished by that? Or would you feel awe? Because the strange thing about the holographic picture is that it does not say the world is fake. It says the world is more than what it appears, that there is a deeper level of description in which everything is connected in ways our intuition cannot easily grasp. Tell me whether the holographic universe excites you or unsettles you, and then come with me into the strangest possibility of all. On number 11, the bounce at the bottom of the dark. When the center becomes a beginning, we have looked at the firewall. We have looked at the fuzzball. We have looked at the hologram. Now we come to a fourth possibility, and in some ways the most extraordinary one. The possibility that the center of a black hole is not an ending at all. The possibility that it is a beginning. The possibility that deep inside the gravitational well, where the equations of general relativity tear themselves apart, what really happens is that spacetime, instead of terminating, bounces. And on the other side of the bounce, a new region of space, perhaps an entire new universe, unfolds. This idea comes from a different approach to quantum gravity, called loop quantum gravity, which has been developed largely outside the string theory community. Loop quantum gravity does not assume strings or branes or extra dimensions. Instead, it tries to take the geometry of general relativity and quantize it directly, treating space itself as having a granular structure at the smallest scales. In loop quantum gravity, space is not a smooth continuum. It is made of tiny discrete units, networks of relationships called spin networks, whose evolution over time builds up the appearance of smooth four-dimensional spacetime. When you apply loop quantum gravity to the interior of a black hole, something remarkable happens. The singularity that classical general relativity predicts at the center is replaced by a region of very high but finite curvature. The matter that fell in is compressed to enormous densities, but not infinite densities. And as the curvature reaches its peak, the quantum nature of space prevents further collapse. The geometry does not crash, it bounces. The infalling matter, having reached a minimum size determined by the granularity of space, begins to expand again. The black hole's interior in this picture contains the seed of an outgoing region, a bouncing universe. A new beginning hidden inside what looked, from the outside, like a final ending. If this is right, then every black hole in our universe contains, on the other side of its central bounce, a region of expanding space. A region that from inside looks like a baby universe being born. The center of a black hole in this view is a transition, a doorway, a place where one cosmos folds into another, and our own universe with its mysterious initial expansion. With its uniformity and its largeness and its baffling beginning, might itself be the interior of a much larger black hole in some still larger universe, the bounce having happened so long ago that we have lost any direct evidence of it. This is not pure speculation. There are real, peer-reviewed papers in serious journals exploring exactly this possibility. The mathematics, while not yet complete, is suggestive. The cosmological consequences, if they could be detected, would be subtle but in principle observable. Some researchers have looked for signatures in the cosmic microwave background, the leftover heat from our universe's early history that might hint at a pre-bounce phase, evidence that our cosmos has a parent. So far, the evidence is inconclusive. But the question is open, and the answer, if it ever comes, would be staggering. Think about what this would mean. Every supermassive black hole at the center of every galaxy, every stellar mass black hole left behind by a dying star, every primordial black hole that may have formed in the chaos of the early universe, would be the womb of another cosmos. Universes nested inside universes, like a fractal, like a strange biological process operating on the scale of geometry itself. Our own existence in this picture would be merely a leaf on a vast and ancient tree of black hole-born universes, with no clear beginning and no clear end. There is a version of this idea that goes even further. The physicist Lee Smolin proposed, more than 30 years ago, a hypothesis he called cosmological natural selection. He suggested that if universes are born from the centers of black holes, and if the laws of physics in each baby universe are slightly different from the parents, then a kind of cosmic evolution might occur. Universes whose laws allow them to produce many black holes would have more offspring. Their descendants would outnumber the descendants of universes that produce few black holes. Over many generations of this cosmic reproduction, the universes that survive would be those whose physical laws are particularly good at making black holes. And our universe, with its apparent fine-tuning, its just right physical constants that allow stars and galaxies and life to exist, would be the natural product of this evolutionary process. This is speculation. It is well-flagged speculation, made by serious physicists, but it remains unconfirmed and may always remain so. We have no direct way to test whether universes are born inside black holes. We have no way, at present, to send a signal across such a hypothetical boundary. And we have no observational evidence yet that our own universe was so born. But the very fact that such an idea is even on the table, that real physicists discuss it at conferences, that it appears in published papers and is taken seriously as a possibility, tells you something profound. It tells you that the answer to the question what is at the center of a black hole may be, in some form, another universe. And that question, the question of whether centers and beginnings are the same thing, is being actively investigated. Take a moment with that. Let it sit. Because the picture you grew up with, the funnel and the point and the crushing weight, gives no hint of this possibility. The funnel ends. The drain reaches its bottom, but the actual physics is moving in a direction where the bottom may not exist, where the center may be the very thing that prevents an ending, where falling all. Tell me below how it lands. Because we are about to take one more step, and the step we are about to take is going to ask you to question whether the very idea of an interior, the very concept of what is at the center, even makes sense. On number 12, the wall that watches you disappear, holographic memory and the information that came back, we have to slow down for a moment and circle back to information. Because the story of information in black holes is, in many ways, the spine of everything else we have discussed. And in the past 5 or 6 years, there has been a quiet revolution in our understanding of where that information goes. A revolution so profound that some physicists are calling it the resolution of the deepest paradox in modern physics, and it bears directly on the question of what, if anything, is at the center. Recall the setup. A black hole forms. Things fall in. Each thing carries information, a unique pattern of particles and states. The black hole, viewed from outside, appears to have only 3 properties: its mass, its charge, and its spin. All the rich variety of what fell in seems to be lost behind a featureless horizon. And then, over long time scales, the black hole evaporates by emitting Hawking radiation, a thermal glow that is, in Hawking's original calculation, completely featureless. If that radiation is truly featureless, and the black hole eventually evaporates to nothing, then all the information that ever fell in has been erased. Quantum mechanics, which holds information sacred, would be violated. Something would be deeply wrong. For decades, this was the paradox. Hawking himself, who first formulated it, believed for a long time that information really was destroyed. He famously made a bet on it with another physicist, John Preskill, in 1997. The terms of the bet were a baseball encyclopedia, of all things, to be given to the loser, with the understanding that if information could be destroyed, Preskill would have lost. In 2004, Hawking publicly conceded the bet. He had become convinced, through arguments involving holography and ADS-CFT and other developments, that information was probably preserved after all. He paid Preskill the encyclopedia. Many physicists felt the matter was at long last settled, but conviction is not proof. And until very recently, no one had a complete calculation showing precisely how the information escapes. The argument relied on principles like the holographic principle, which gave strong reasons to believe information was preserved, but did not show the mechanism in detail. For years, this was a frustrating gap. The principles said one thing, the original calculation by Hawking said another, and no one could reconcile them in a fully convincing way. Then, beginning in 2019, a series of breakthrough papers appeared. The work of physicists like Jeff Pennington, Ahmed Almeri, Donald Maroff, Henry Maxfield, Netta Engelhart, and others. They developed a technique called quantum extremal surfaces, a way of computing the entanglement entropy of Hawking radiation that included contributions from regions deep inside the black hole. These regions, called entanglement islands, captured the way the interior of the black hole was quantum mechanically connected to the radiation outside. And when you included these islands in the calculation, the result was startling. The entropy of the Hawking radiation, far from increasing forever as Hawking had calculated, eventually peaked and began to decrease. The pattern was exactly the page curve, the entropy curve that information preservation requires. The math, for the first time, agreed with the principle. Information was not just preserved as a matter of faith. Information was preserved as a matter of calculation. The page curve was no longer a hope, it was a result. What does this mean physically? It means that as a black hole evaporates, its interior, what used to be thought of as a separate region behind the horizon, becomes progressively more entangled with the outgoing radiation. Eventually, the interior and the radiation outside are so entangled that, in a meaningful sense, the interior is not separate anymore. The information that fell in has effectively been transferred to the outside, encoded in subtle correlations between the particles of the radiation. And by the time the black hole has fully evaporated, all of that information is, in principle, recoverable from the radiation that has been emitted. Now think about what this implies for the center. If the interior of a black hole is, over time, smoothly transferring its contents to the surrounding radiation, then the center is not so much a fixed location as a slowly emptying region. The information that fell in is not sitting there forever, locked away. It is leaving gradually by a route we did not previously appreciate. The center is, in some sense, a process, a slow exhalation, an emptying, and this connects back to the holographic picture in a beautiful way. Because the way the interior is entangled with the radiation suggests that the deep interior, including whatever is at the center, was always, in some sense, encoded outside. The boundary always had the full content. The interior was always a kind of dual description. And as the black hole evaporates, the duality is gradually resolved in favor of the boundary description, until the interior, having handed over all its information, simply disappears. This is not a complete picture. There are still many open questions. How exactly the information gets out, the precise mechanism by which it is encoded in the Hawking radiation, is still being worked out. There are still debates about how the various pictures, firewalls, fuzzballs, holograms, bouncing universes fit together, or whether some of them are inconsistent with the new results. The story is moving, but the direction of the motion is clear. The center of a black hole is not, in modern thinking, a static repository of crushed matter. It is a dynamic, slowly evaporating, deeply entangled, holographically encoded region whose boundary with the outside is more porous than we ever imagined. And the philosophical implications of this are, in a quiet way, enormous. Because the version of you that falls into a black hole in this picture is not annihilated. The information that constitutes you, every quirk and pattern and structure that made you, is preserved. Slowly, over timescales that exceed the current age of the universe by huge factors, that information would be carried back out, particle by particle, in the radiation that the black hole emits. You would not survive in any recognizable sense. You would be unspooled, scrambled, encrypted in correlations that would take longer than the age of the cosmos to read. But the pattern, the deep pattern of you, would not be lost. It would return to the universe, eventually, in a form so distributed and so entangled that no one and nothing could ever reassemble it. And yet, in the strict mathematical sense, it would still be there. That is, in some ways, an oddly comforting thought. The universe does not destroy what falls into its darkest places. It only hides it, beyond all practical recovery, for a length of time so vast it might as well be forever. But the information remains. The pattern persists. And the black hole in the long view of cosmic history is not a grave but a vault, sealed, slow, and in time opening. So let me ask you, does it feel different to imagine the inside of a black hole as a vault rather than a grave? Does the preservation of information, even in a form no one could ever read, change how the object feels to you? Some people find this comforting in a way they did not expect. Others find the timescales too vast for it to matter. Tell me where you land. And then, finally, we will descend through the last layers, the layers where the question of the center itself begins to dissolve. On number 13, the tunnels beneath the math, wormholes, hidden connections, and the geometry of entanglement. Before we make our final descent, we have to talk about one more piece of the puzzle, a piece that has been growing in importance over the last decade, and that ties together several of the proposals we have already discussed. The piece is called the relationship between entanglement and geometry, and the bold claim, made by some of the most respected theoretical physicists working today, is that the very fabric of spacetime, the smooth fabric that gravity bends and curves, is woven out of quantum entanglement at its deepest level. That what we call distance, what we call separation, what we call inside and outside, are all manifestations of patterns of entanglement among the underlying quantum degrees of freedom. This idea is sometimes summarized in a slogan, ER equals EPR. ER stands for Einstein-Rosen, the two physicists who, in 1935, proposed a mathematical structure called an Einstein-Rosen bridge, which we now usually call a wormhole. A wormhole, in classical general relativity, is a hypothetical tunnel through spacetime, a shortcut connecting two distant regions through a fold in the geometry. EPR stands for Einstein-Podolsky, and Rosen the same Einstein and two collaborators, who in the same year 1935 proposed a thought experiment about quantum entanglement, the phenomenon where two particles can share a quantum state such that measuring one instantaneously affects the other, no matter how far apart they are. For nearly 80 years, these two concepts, wormholes and quantum entanglement, were considered totally separate. One was a feature of general relativity, the smooth geometric theory. The other was a feature of quantum mechanics, the granular probabilistic theory. They had nothing obvious to do with each other. They were both proposed by Einstein in the same year, but the connection seemed accidental. Then, in 2013, Juan Maldacena and Leonard Susskind put forward a remarkable conjecture. They suggested that entangled particles are connected by tiny wormholes. That the geometric structure of a wormhole, the bridge through spacetime, is in fact the same thing as the quantum mechanical entanglement between two systems. Two black holes that are quantum mechanically entangled are connected by a wormhole in spacetime. Two electrons that are entangled are connected, in some deeply hidden sense, by a microscopic wormhole. Geometry and entanglement in this picture are two descriptions of the same underlying reality. This idea has had enormous consequences in the years since it was proposed. It is part of why the page curve calculations work. It is part of why the holographic principle is taken so seriously. It suggests a way to understand how black hole interiors can be both behind a horizon and yet entangled with the outside, because the wormhole connecting interior to exterior is just the geometric expression of the entanglement. And it suggests, more broadly, that spacetime itself is not fundamental. Spacetime in this view is an emergent phenomenon, a structure that comes into being when quantum systems become sufficiently entangled. Where there is little entanglement, there is little spacetime. Where there is much entanglement, smooth and extended geometries emerge. The shape of the universe, including the bending of spacetime around mass and energy, is a kind of structured pattern of underlying quantum correlations. If this is right, and it is still a conjecture, although a very fertile one, then the question of what is at the center of a black hole takes on yet another twist. Because the center, if it exists, is connected by entanglement, and therefore by tiny wormholes to the outside, the interior is not a sealed-off region. It is a region whose connection to the outside is so deep, so woven into the very fabric of geometry, that the distinction between in and out becomes harder to maintain at the most fundamental level. The center is, in a sense, everywhere, or nowhere, or somewhere that does not quite map onto our usual ideas of place. And this connects, finally, to a possibility that has begun to circulate more widely in recent years. The possibility that what we call the center of a black hole is not really a center at all. That the very concept of a deep interior, separated from the rest of the cosmos by an impenetrable horizon, may be a feature of our outdated thinking. That the new picture, the one that emerges from holography and entanglement and the page curve, is one in which black holes are deeply integrated into the structure of the universe at every scale. They are not isolated objects with secret cores. They are highly entangled regions whose contents are, in principle, accessible everywhere, even if no one has the technology to read them. In 2025, in a paper that drew wide attention, a team of physicists led by Raul Carballo-Rubio proposed a non-singular paradigm of black hole physics. They argued, building on a growing body of work, that real black holes are likely to lack singularities entirely, and that the classical singularity is an artifact of an idealized theory that does not apply to the actual quantum world. Other recent work, published in 2025 in journals like Physics Letters B and Physical Review D, has explored what are called regular black holes, models in which the interior is smooth all the way through, with no singularity at all. These models suggest that what falls in does not crash into a point. It enters a region of high but finite curvature, possibly oscillates, possibly bounces, possibly emerges, but never reaches infinite density. The interior in these models is exotic and strange, but it is bounded and finite, and it is full of physics rather than empty of it. There is no single accepted picture yet. The field is alive. The disagreements are real, but the trajectory of modern thinking is clear. The singularity is dying. The point at the bottom of the funnel is being replaced, in proposal after proposal, by something richer and stranger and more spacious. The center, if there is one, is not a flaw in spacetime. It is a region of physics we are only beginning to understand. So let me ask you, after all of this, do you feel that we are closer to understanding what is at the center of a black hole or further away? Some people feel that the proliferation of theories means we know less than we thought. Others feel that the convergence on themes like the absence of a singularity, the role of information, the holographic encoding, means we are circling in on a real answer. Tell me where you stand. And then finally, let us walk together into the last room, the one where the question itself begins to dissolve. On number 14, the center that was never a place, the dissolution of the question. Now we come, slowly, to the part of the night where we stop falling and begin to float, because we have descended through layer after layer of theory, each one revealing the previous to be incomplete. The funnel was wrong. The point at the bottom was wrong. The singularity was wrong, or at least misleading. The firewall, the fuzzball, the hologram, the bounce, the wormhole, the regular black hole, the entanglement island. Each of these is a different way of trying to describe what we cannot directly see. And the deeper we have gone, the more the original question, the question of what is at the center, has begun to lose its shape. Because what does it mean to ask what is at the center of an object whose interior is, by its very nature, an extension of its surface? What does it mean to ask what is in the middle of a region of spacetime, where the very concepts of middle and edge break down at the quantum level? What does it mean to ask what is at the center of a black hole, when the answer might be that the question itself is built on assumptions that the actual physics rejects? The deepest answer, the one that is emerging from contemporary research, is not that there is something specific at the center of a black hole. The deepest answer is that the center, in the sense we usually mean, is a concept that does not fit. There is no there. There is no point in space where the matter accumulates. There is no chamber, no core, no nucleus. What we have instead is a region of spacetime where the geometry, the information, and the matter are all woven together in ways that do not separate cleanly into inside and outside, center and surface, before and after. The black hole is not, in modern thinking, a container with contents. It is a structure, a process, a configuration of the universe whose interior is part of its boundary, whose information is part of its surroundings, whose past is part of its future, and whose future is, in some real sense, the universe's future. This is not a way of saying the question was meaningless. The question, when you first asked it, was the right question. It is the question that drove all of these investigations. It is the question that produced the photographs, the gravitational wave detectors, the singularity theorems, the holographic principle, the page curve. It is the question that pulled humanity from a vague picture of dark wells in space to a rich, contested, evolving picture of the most extreme objects in the universe. The question was good. The question opened the door. It is just that, walking through the door, we have found that the room beyond does not have the shape we expected. The room is larger than the question. The room contains the question and dissolves it. Let me try to put this another way. When you ask what is at the center of a black hole, you are imagining a black hole as a kind of solid object in space, with an interior that has its own geography, its own up and down, its own privileged middle. But none of those things, it turns out, are properties of a black hole. The interior does not have a middle in the way a room has a middle. The interior has time. It has a future. It has, perhaps, a transition. But it does not have a center in any sense that maps onto the centers of ordinary things. The very word center, when applied to a black hole, is a metaphor borrowed from objects that do not behave like black holes at all. If you must have an answer, then, in modern physics, the answer would be something like this. At the place where general relativity says a singularity should be, there is instead a region of extremely high curvature, almost certainly finite, where quantum gravitational effects dominate. That region may bounce into a new region of spacetime. It may dissolve into a fuzzball of stringy structure. It may be a holographic projection of information stored on the horizon. It may be all of these in different formalisms, depending on which questions you ask and which mathematical tools you use. And the information about what fell in is, in the long run, not destroyed. It is encoded, somewhere between the deep interior and the radiation that the black hole emits, in a way that preserves the principles of quantum mechanics even though, in practice, that information is utterly inaccessible to any conceivable observer. The center of a black hole, in short, is a question that physics is in the process of answering by reformulating it. We are not, in this generation, going to be told that there is a tiny crushed ball of matter at the center, the way our childhood books suggested. We are going to be told something more like this. The matter that fell in has been transformed into a different kind of stuff, in a different kind of space, possibly in a different kind of universe, and its information is in the process, however slowly, of being returned to the cosmos. Black holes are not graves. They are not even quite places. They are processes. Long, slow, almost unimaginably slow processes of cosmic recycling. And here is the thought I want to leave you with before we wind down. Every black hole in the cosmos is going through this process right now. As you listen to this, the supermassive black hole at the center of our galaxy, Sagittarius A star, is emitting Hawking radiation, very faintly because of its size. The colossal black hole at the center of M87 is doing the same. Every stellar mass black hole left behind by every dead star is doing the same. They are all evaporating, all leaking information, all participating in this slow exhalation of the universe. The timescales are enormous. A supermassive black hole would take something like 10 to the 100th power years to fully evaporate, far longer than the universe is old. But the process is happening. The center, whatever it is gradually becoming the surface. The surface is gradually becoming the radiation. The radiation is gradually becoming the universe again. There is a quiet beauty in that. The most extreme objects in the cosmos, the ones that swallow stars and bend light into circles and freeze time at their boundaries, are, in the very long run, returning everything they took. Not in any form we could ever recognize, but in a form that, by the deepest laws of physics, still carries the memory of what was lost. So let me ask you, do you feel different about black holes now than you did when we started? Has the funnel given way to something else in your mind? When you imagine one now, what do you see? A wall of fire, a fuzzball, a hologram, a bouncing universe, a slowly evaporating vault of cosmic memory, a process that is part of the long breath of the cosmos. Tell me what image has replaced the old one, because that image, whatever it is closer to the truth than the one you started with. And the journey it took to get there is the journey humanity has been on for 100 years and is still on. On number 15, the cosmos inside the cosmos, the strange hypothesis that we are already inside one before we close, before we let the night settle and the questions soften, there is one more idea to sit with. It is the strangest of them all. And it has been growing slowly, from the fringes of theoretical physics toward something more mainstream over the past several years. It is the idea that the universe we inhabit, the entire cosmos of stars and galaxies and dust and life, and you sitting wherever you are right now listening to this, might itself be the interior of a black hole. A black hole in some larger parent cosmos that we cannot see and may never be able to detect. This sounds at first like science fiction. It is not. The idea has serious mathematical roots, and in recent years has appeared in peer-reviewed papers exploring the consequences of certain models of quantum gravity, particularly models in which black hole interiors can give rise to expanding regions of spacetime. If the bounce models we discussed earlier are correct, if the center of a black hole really is a transition into a new region of spacetime, then it is at least consistent to ask whether our own universe was born this way. Whether our Big Bang was, from the outside, the formation of a black hole in some larger reality. There is a peculiar piece of arithmetic that gives this idea a kind of strange respectability. If you take the total mass of our observable universe, including all the matter and energy we can measure, and you compute the Schwarzschild radius corresponding to that mass, the size that a black hole of that mass would have, you get a number that is eerily very close to the size of the observable universe itself. Make of that what you will. It may be a coincidence. It may be a deep clue. It is the kind of numerical hint that catches the attention of theoretical physicists and sends them down long roads of speculation. If we are, in fact, inside a black hole, what would that mean? It would mean that our universe is finite, with a boundary defined by the parent black hole's event horizon. It would mean that everything that exists for us is, from the parent universe's perspective, a region of trapped light, a place from which no signal can ever escape back to the outside. It would mean that the Big Bang was not the absolute beginning, but the moment when the bounce occurred, when the matter falling into the parent black hole reached the quantum gravitational threshold and began to expand into a new region. And it would mean that the future of our universe, the slow expansion that we observe, is the unfolding of an interior that, to anyone watching from outside, is just the inside of a colossal black hole, drifting in a far larger sea of cosmic space. This idea has been around in various forms since the 1970s, but it has gained renewed attention recently. Late in 2025, the science press carried multiple stories on the possibility that recent observations, particularly the strange uniformity of the cosmic microwave background and the patterns in early galaxy formation observed by the James Webb Space Telescope, are at least compatible with our universe being a black hole interior. The evidence is far from conclusive. It is, in the most honest framing, suggestive. It is the kind of evidence that motivates more research rather than proving anything. But the conversation is happening. The papers are being written. The hypothesis is being tested against new data as it comes in. What is so vertigo-inducing about this picture, when you really let it settle, is what it implies about your relationship to the cosmos. You, in this picture, are inside the very kind of object we have been discussing all night. You are right now in the interior of a black hole. The walls of that black hole are so far away, in space and in time, that you can never reach them. The center, if there is one, may be either far behind you, in the moment of the Big Bang, or far ahead of you, in some future you cannot conceive. The black hole is your universe. The universe is your black hole. And the question of what is at the center of a black hole becomes, in some sense, the question of what is at the center of everything. This is not a claim we should be too confident about. It is a possibility, one among several. But it is a possibility that real, working physicists take seriously, and that is itself a remarkable thing. A century ago, the idea that the universe might be inside a black hole would have been considered nonsense. Today, it is a published research direction. The line between what is fringe and what is mainstream in cosmology has shifted, and shifted significantly, as our tools have improved and our theories have matured. And here is the gentle, almost philosophical implication of all this. If we are inside a black hole, then the dichotomy between observer and object collapses. We are not looking at black holes from the outside. We are looking at them from the inside, all the time. Every star we see, every galaxy, every patch of cosmic background, is part of the interior we have been trying so hard to understand. The mystery we have been trying to penetrate is, in this picture, the mystery of our own home. There is something almost domestic about this idea when you let it settle. The black hole, the most alien object in the universe, the place we have struggled to picture, might be the very place where everything happens. The cosmos itself, your room, the stars overhead, the pulse of your own heartbeat, all inside. So let me ask you, if you knew with certainty that the universe was the inside of a black hole, would the universe feel different to you? Would the night sky look different? Would your own life feel more contained or more strangely free? Some people, when they first encounter this idea, find it claustrophobic. Some find it liberating. Some find it beautiful, in a way that has nothing to do with claustrophobia or freedom, but is closer to a kind of cosmic intimacy. Tell me which response feels most like yours. And then, Gently, we will begin the long, slow wind toward the close of this night. On number 16, the slow echo beneath the surface, what future detectors might hear before we let everything dissolve into philosophy. Let us touch the ground one more time and talk about what humanity is actually doing right now to learn more about the centers of black holes. Because the work is not finished. The conversation we have been having is not just a debate among theorists. It is a debate that is, slowly, becoming testable. And the next 2 decades of physics may give us empirical answers to questions that, until recently, seemed forever out of reach. The first frontier is gravitational wave astronomy. The Laser Interferometer Gravitational Wave Observatory, LIGO, which began detecting gravitational waves in 2015, has now recorded scores of black hole mergers. Each one is a brief chirp in our detectors, a rising whistle as 2 black holes spiral inward and collide. From these signals, we can measure the masses, the spins, the distances, the geometries of the merging objects. And in the final fractions of a second, the so-called ringdown phase, when the newly merged black hole settles into its final shape, the signal carries faint information about the structure of the new black hole's horizon and the regions just beneath it. In recent years, several teams have proposed looking, in this ringdown signal, for what are called gravitational wave echoes. The idea is that if a black hole has any kind of internal structure just inside the horizon, any solid surface or quantum membrane or sudden change in geometry, then a small fraction of the gravitational wave energy might reflect off that structure and arrive at our detectors slightly after the main signal. A second wave, a faint repeat, delayed by milliseconds. So far, the searches have not produced any clear, confirmed echoes. The mergers we have observed are consistent with classical black holes, with smooth event horizons and no obvious internal features. But the sensitivity of our detectors is improving rapidly. The current generation of LIGO will be joined, in the coming years, by upgraded instruments and entirely new observatories. The Einstein telescope, a planned underground gravitational wave observatory in Europe, will be 10 times more sensitive than the current LIGO. The Cosmic Explorer, a planned facility in the United States, will be similarly powerful. And in space, the Laser Interferometer Space Antenna, LISA, scheduled to launch in the next decade, will be able to detect entirely different classes of gravitational waves, including those from supermassive black hole mergers at the centers of galaxies. With these new tools, we will be able to look for echoes, for departures from classical predictions, for subtle hints of what lies just inside the horizon, with a sensitivity we cannot currently match. The second frontier is the next generation of the Event Horizon Telescope. The original EHT, with its 8 ground-based radio telescopes, gave us the first photographs of M87 and Sagittarius A star. Plans are already underway to expand the array, to add new wavelengths, to incorporate space-based components, and eventually to produce not just still images but high-fidelity movies of accretion flows around black holes. These observations will probe the immediate environment of the horizon in unprecedented detail, and they may reveal subtle deviations from the predictions of classical general relativity, deviations that would hint at quantum gravitational effects in the deep interior. So far, every observation has been beautifully consistent with Einstein's theory. But the question is whether, at higher precision, cracks will begin to appear. The third frontier is theoretical. The work of computing the page curve, of mapping out the geometry of entanglement, of building consistent models of regular black holes without singularities, is moving forward rapidly. Papers appear every month. Conferences are held every year. Younger physicists are entering the field with new tools, new mathematical techniques, new connections to other areas of physics. The intellectual ferment around black holes today is comparable to the ferment around quantum mechanics in the 1920s or relativity in the 1915s. It is a moment of active discovery, a moment when textbooks are being rewritten in real time. And the fourth frontier, perhaps the most surprising one, is cosmological. The James Webb Space Telescope, launched in 2021 and operating now for several years, has been observing the very early universe with unprecedented precision. It has spotted galaxies that formed remarkably early, including a population of objects that have been called little red dots, which may be early supermassive black holes still in the process of growing. By studying how these black holes formed, how quickly they grew, how they relate to the galaxies around them, we are learning new things about the cosmic history of black hole formation. And there is at least some chance that, in the patterns of these early objects, we will find clues about the deep nature of black hole interiors, maybe in their growth rates, maybe in their accretion signatures, maybe in subtle correlations that, taken together, hint at processes happening deep inside, processes that connect to the questions we have been discussing. In short, the question of what is at the center of a black hole is not going to remain a purely theoretical question forever. It is becoming, slowly, an observational question. The instruments we are building, the data we are gathering, the theories we are refining, are all converging on a moment, perhaps within the next 20 or 30 years, when we will have empirical answers to questions that previously could only be addressed by argument and conjecture. The journey we have taken tonight, through firewalls and fuzzballs and holograms and bouncing universes, will not always be a journey through possibilities. Some of these possibilities will be ruled out. Some will be confirmed. Some, perhaps, will be replaced by ideas no one has yet thought of, ideas that will require new mathematics and new physics to even articulate. And that, in the end, is one of the most exhilarating things about being alive at this moment. We are in the middle of a story that is still being written. We are not at the end of physics. We are not even close. The questions that fascinated Einstein, the questions that drove Hawking and Penrose and the generations after them, are still open. And they may, in our lifetime, begin to close. We may live long enough to read the headlines that say, finally, here is what the inside of a black hole really looks like. And whatever that headline reports, it will be something we could not have predicted from where we are now. So let me ask you, do you think we will solve the puzzle of black hole interiors in your lifetime? Do you think future generations will look back at us, at this moment, as the people who lived just before the answer came? Or do you think the question will turn out to be deeper, harder, more endless than we currently realize, requiring centuries of further work? Tell me your prediction. There is no way to be wrong because no one knows, but it is good, sometimes, to commit to a guess, to stake a small flag in the dark and say, here is where I think it will end. And then to see, over the years, whether the flag still stands. On number 17, The Long Wind Down, a recapitulation in the voice of a dreamer, let me tell you what we have done tonight, not as a summary, not as a list, but as a small, quiet retelling in the manner of a friend looking back at a long walk together. Because we have walked a long way, and the path behind us is worth gently retracing before we step away from it. We began with a picture, the cartoon black hole, the funnel in space, the drain that swallows stars. We carried that picture with us from childhood, through schoolrooms and storybooks and films, and we accepted it without much question, because everyone around us seemed to accept it too. And then we took the picture in our hands, and we looked at it carefully, and we noticed that it had no relationship to anything real. There was no funnel. There was no spiral of gas dripping down into a tiny point. There was a sphere of darkness, surrounded by a ring of light bent into a halo by gravity. Two real photographs, both taken in our own century, had shown us this. And the funnel, the comfortable funnel, was gone. We followed Einstein into his geometry. We saw how gravity was not a force but a curving of spacetime, and how that curving, in the equations Karl Schwarzschild wrote down in the trenches of a war he would not survive, produced a strange peculiarity at a particular distance from a sufficiently dense mass. We watched as decades of observation, from binary X-ray sources to the orbits of stars near the heart of our galaxy, slowly convinced the scientific world that black holes were not just mathematical curiosities. They were real. They were everywhere. They were part of the inventory of the cosmos. We then crossed, in imagination, the event horizon. We learned that the horizon is not a wall, not a surface, but a tilt in the geometry, a place where every direction begins to point inward and the center becomes not a place but a future. We learned that for a large enough black hole, the crossing would feel like nothing at all, but that the descent would gradually steepen, until the body of any falling observer would be drawn into a thin filament, and then, at the very end, into a stream of particles falling forever inward. We then came to the singularity, the point at the bottom of the funnel that in our childhood image had been the answer, and we saw that the singularity in the actual physics is not an answer. It is a confession. It is the place where our theory breaks. It is an infinity that history tells us is always a sign of incomplete understanding. And we walked slowly through the four leading proposals for what really lives in the place where the singularity is supposed to be. We saw the firewall, the wall of fire at the threshold, demanded by certain arguments about how information must flow in a quantum mechanical world, and threatening the smooth crossing that Einstein's geometry seemed to promise. We saw the fuzzball, the dense, structured tangle of strings and brains that fills the entire interior with rich quantum substance, eliminating the singularity by filling everything to the brim. We saw the hologram, the astonishing idea that the interior of a black hole, and perhaps the interior of any region of space, is encoded on the surface that surrounds it, that what we call depth is a kind of dual description of information that lives in a boundary. And we saw the bounce, the possibility that the center of a black hole is not an ending but a beginning, a transition into a new region of spacetime, perhaps a new universe, born from the collapse of the old. We traced, briefly, the recent breakthroughs in the information paradox, the slow accumulation, beginning around 2019, of evidence that information is not destroyed in black holes after all, that the matter that falls in, scrambled and stretched and unraveled, eventually leaves again in the slow trickle of Hawking radiation, in a form so distributed and so encrypted that no one will ever read it, but in a form that, in principle, is still there. The black hole as a vault, not a grave. The center as a process, not a place. We touched the conjecture that entanglement and geometry are the same thing, that the very fabric of spacetime is woven from quantum correlations among underlying degrees of freedom, that the inside and outside of a black hole are not separate worlds, but two views of a single, deeply entangled structure, that the center, in some real sense, is everywhere and nowhere, and the question of what is in it dissolves into a deeper question about the nature of space and time themselves. And we faced, finally, the strange possibility that our own universe is the interior of a black hole in some larger cosmos, that the descent we have been imagining, the long fall through curving geometry, is something we are always already doing, that we are, in some sense, inside the question we have been asking. That is the journey, that is the path we walk tonight. And looking back at it, you can see, I hope, that the original question, the question of what is at the center of a black hole, was a doorway. It looked, when you first asked it, like a question with a single answer. A list of possible objects you could imagine finding there. A small thing like a marble or a point or a crushed ball of matter. But the question, walked into, has opened out into something much larger, into the structure of spacetime, into the nature of information. into the relationship between gravity and quantum mechanics, into the possibility that the cosmos we live in is itself the kind of thing we have been studying, and it has been worth the walk. Every step has been worth it. Because even if we never get a clean, final answer, even if the question keeps unfolding into deeper questions, the unfolding is itself a kind of answer. The unfolding tells us something about the universe we live in. It tells us that the universe is deeper than its surface, that the obvious picture is almost never the true picture, that the most familiar things, when you look at them carefully enough, are stranger and more interesting than you had any reason to suspect. So now, with the path behind us, let me ask you one more time. Of all the layers we have descended through tonight, which one stayed with you most? Which one will you remember tomorrow morning when the sun comes up and the practical demands of your life return? The firewall, the fuzzball, the hologram, the bouncing universe, the slow exhalation of information, the cosmos as a black hole's interior. Tell me which one stuck, and then come with me gently into the closing of this long night. On number 18, the soft landing, where the question ends and the wondering begins, we are, I think, near the end of our walk. The sky outside, wherever you are listening, may be quiet now. The world may be still. The small, ordinary noises of the place you are in, the hum of a refrigerator, the soft breathing of someone you love asleep in another room, the rustle of a leaf against a window. All of those small noises are continuing as they always do, while the cosmos turns on its great slow axis above them. And here is what I want you to remember when you turn off this video and lie down to sleep tonight. The question we asked at the beginning was a question about an object. What is at the center of a black hole? We tried to answer it as if there were a definite, concrete, locatable thing waiting for us at the bottom of a well. And what we found instead was that the question was bigger than we knew, that the answer is being written, even now, in the working papers of physicists across the world, and that the answer, when it finally comes, will not be a thing. It will be a way of seeing. The center of a black hole, in the picture that is emerging, is not where the matter ends up. It is where our concepts begin to break and reform. It is where space and time, those most basic ideas, lose their familiar meaning and become something else. It is where information, the thing we never knew was a physical quantity until recently, is encoded and transferred and ultimately returned. It is where the universe shows us, more clearly than anywhere else, that the surface and the depth, the inside and the outside, the part and the whole, are not as separate as our daily experience tells us. The black hole, at its deepest, is a teacher. It teaches us that reality is not built the way we instinctively assume, and it teaches us, in a quieter way, something about ourselves. Because the matter that falls into a black hole, the stars and clouds and atoms that have spent their long lives drifting through the cosmos, they are, in the most fundamental sense, made of the same stuff that you are made of. The carbon in your bones, the iron in your blood, the oxygen you are breathing right now, every atom of you was made in the heart of an ancient star, and many ancient stars ended their lives by collapsing into black holes. You are, in a real and literal way, a survivor of the same kind of cosmic violence that produces the objects we have been talking about all night. The line between you and them is not as clean as the dark photograph would suggest. You are, in part, the cousin of every black hole. The matter of you is older than this planet, older than the sun, and it has come from the same fiery cradles. And one day, very far in the future, every black hole in this universe will finish its evaporation. Even the largest, even the supermassive ones, will eventually, after timescales so vast they exceed the current age of the cosmos by factors that strain the imagination, leak away into Hawking radiation. The matter that was once stars, the matter that was once planets, the matter that was, perhaps in some distant world, once living creatures gazing up at their own night sky, will all be returned to the universe as faint, scattered, encrypted whispers of radiation. Nothing in this cosmos is permanent, not even its darkest objects. Everything is in motion. Everything is in the process of being recycled. And the slow exhalation of every black hole is part of the deep music of the universe, a music we are only beginning to hear. When you imagine a black hole now, I hope you do not see a funnel anymore. I hope you see something else. A sphere of dark sky surrounded by a halo of light. A region of spacetime where the geometry has tilted so far that falling becomes a direction in time. An interior that is not really separate from its surface. A slow process of encryption and return, woven into the long history of the cosmos. A place that, despite everything, is not silent. A place that is, in the deepest sense, in conversation with the universe around it. And if I can leave you with one image, let it be this. Picture yourself lying down, eyes closed, feeling the quiet hum of being alive. Around you, the building. Beyond the building, your city. Beyond your city, the country you live in. Beyond the country, the curve of the earth. Beyond the earth, the sun. Beyond the sun, the spiral arm of our galaxy. Beyond our galaxy, the local group of galaxies. Beyond the local group, the great cosmic web of clusters and superclusters and voids. And somewhere in the middle of our own galaxy at the place we call Sagittarius A star, there is a sphere of dark sky 4 million times the mass of our sun, holding within it the fates of everything that has ever fallen in and slowly exhaling those fates back into the cosmos in the form of a glow we cannot yet detect. The black hole is not separate from you. The black hole is part of the system you are in. The fabric of spacetime that holds you, that lets you breathe and lets your heart beat, is the same fabric that bends so steeply at the heart of the galaxy that light cannot escape. You are not above it. You are not below it. You are inside the same cosmos. That is, in the end, the deepest answer to our question. What is at the center of a black hole? The answer is that, in the most profound sense, you are, not your body, not your atoms, but the same fundamental fabric, the same spacetime, the same quantum stuff. The center of the black hole is made of the same nothing and everything that you are made of. And the cosmos, in its strange way, has been showing you yourself all along. If you have enjoyed walking through this long night with me, a quiet like or subscribe really helps the channel grow. It is a small thing for you, but a meaningful thing for me, and it lets me keep making videos like this one for nights like the one you are in. Now, let your shoulders drop. Let your breathing slow. Let the questions soften into the dark. The universe will keep turning. The black holes will keep slowly exhaling. The stars overhead, wherever you are, will keep tracing their long ancient arcs through the sky. And you, small and conscious and tucked into a small corner of a vast and patient cosmos, are part of all of it. Sleep well under the stars. Wherever you are, whatever your tomorrow holds, the universe has held you all the way through, and it will hold you tomorrow and the night after and the night after that. The center of every black hole is, in some quiet sense, the place where the cosmos remembers what it has been. And you, breathing slowly now, are part of what it remembers. Good night.